In this section of Chapter 2, we will discuss graphs that can be used to better understand our data. In this section of Chapter 2, we will look at other common graphs that we can use to help us better understand our data. We will also discuss other graphs that can be deceptive or create an impression about the data that are misleading or wrong. And finally, we'll be introduced to some technology that provides us with powerful tools for generating a wide variety of graphs. A dot plot is a graphical display of quantitative data using dots. A dot plot, also called a dot chart or a strip plot, is a type of simple histogram-like chart used in statistics for relatively small data sets, where values fall into a number of discrete classes or categories. A dot plot is similar to a bar graph because the height of each bar of dots is equal to the number of items in a particular category. To draw a dot plot, simply count the number of data points in a class and then draw a stack of dots that are that high for that class. Some features of a dot plot are: dot plots display the shape of the distribution of the data set, and also it usually is possible to recreate the original list of data values from the dot plot. For example, from this dot plot, we know that the original data set had one value of 40, a data point at 42, it had 2 data points at 50, and 5 data points at 52, and so on. A stem plot or a stem and leaf plot is also like a histogram. They are both tools to help you visualize a data set. Stem plots show a little more information than a histogram and have been a common tool for displaying data since the 1970s. They are typically used when there is a medium number of quantitative variables to analyze. Stem plots of more than 50 observations are unusual. We call this graph a stem plot because there is one stem with the largest place value digits to the left of the bar and one leaf to the right of the bar. Some features of a stem plot include: stem plots show the shape of the distribution of the data. Stem plots retain the original data values in the data set, and the sample data are sorted or arranged in order. In this example, we see that our stems are the numbers to the left of the vertical bar. They include the numbers 4, 5, 6, 7, 8, 9, and 10. On the right side of the vertical bar are the leaves. The first few values from this stem plot are 40, 42, 50, 52, 52, etc. Stem plots were widely used before the advent of the personal computer, as they were a fast way to sketch data distributions by hand. They are used less frequently today, but you still see some here and there. A time series graph displays values against time. They are similar to an XY graph, but while an XY graph can plot a variety of X variables, for example, height, weight, or age, a time series graph can only display time on the X-axis. The time series graphs do not have categories. Time series graphs are good for showing how data change over time. The goal of the time series analysis is to find patterns in the data and use the data for predictions. An important feature of a time series graph is that it reveals information about trends over time. A bar graph is a graph with rectangular bars. The bars of the bar graph have equal width to show frequencies of categories of qualitative data. The bars may or may not be separated by small gaps. Although the graph can be plotted vertically with the bars standing up, or horizontally, bars laying flat from left to right, the most usual type of bar graph is the vertical. The horizontal x-axis represents the categories, and the vertical y-axis represents the value of those categories. A bar graph is usually looking at a set of data and making comparisons. For example, in this bar graph, it's easy to see which type of movies are preferred by the sample and which types are not. A Pareto chart is a bar graph for categorical data, with the added stipulation that the bars are arranged in descending order according to frequency. So the bars decrease in height from left to right. Features of a Pareto chart are that it shows the relative distribution of categorical data so that it is easier to compare the different categories, and it draws attention to the more important categories. A pie chart is a very common graph that depicts categorical data as slices of a circle, in which the size of each slice is proportional to the frequency count of the category. In other words, each slice of the pie is relative to the size of that category in the group as a whole. The entire pie represents 100% of a whole, while the pie slice represents the proportion of the whole pie. The pie charts give you a snapshot of how a group is broken down into smaller pieces. An important feature of a pie chart is that it shows the distribution of categorical data in a commonly used format. A frequency polygon is a graph using line segments connected to points located directly above class midpoint values, and it is very similar to a histogram, but a frequency polygon uses line segments instead of bars. Frequency polygons can be used to compare more than one data set or to display a cumulative frequency distribution. A frequency polygon uses line segments connected to points located directly above the midpoint values. The midpoint value of each class is labeled on the x-axis. The y-axis of the graph will mark the frequency of each class. If we look back at our McDonald's frequency distribution, we see that the first class of 175 to 124 seconds is represented on the x-axis with the midpoint of 99.5. Recall that we calculated that midpoint for our classes in a previous section. The point above 99.5 represents the frequency of times that were between 74 seconds and 124 seconds. And so we can record those 11 service times at the midpoint of 99.5. As I mentioned before, frequency polygons can be used to compare more than one data set. Comparing two histograms would be more difficult since we would have to draw the rectangles of the two data sets on top of each other. Because frequency polygons are just lines, they do not pose the same problem. In this frequency polygon, we can compare the lunchtime service of McDonald's to the lunchtime service of Dunkin' Donuts. Here we can see that in general, service times at lunch are faster at Dunkin' Donuts. A common deceptive graph involves using vertical scale that starts at some value greater than 0 to exaggerate differences between groups. In this example, the two graphs are based on the same set of data from a clinical trial of OxyContin. By using a y-axis or the vertical scale that starts at 10% instead of 0, the differences between the treatment group and the placebo group are grossly exaggerated. With the graph starting at 10%, it appears that those using OxyContin experience nausea at a much higher rate, that is about 12 times higher than the placebo group. But when we look at the graph that starts at 0, it shows the actual ratio, which is only about 2 times higher. So regardless of the reason for displaying a graph with a non-zero axis, it is important to be aware of the non-zero axis so that you can avoid being deceived by the graph. A pictograph uses picture symbols to convey the meaning of statistical information. Pictographs should be used carefully because the graphs may either accidentally or deliberately misrepresent the data. Data that are one-dimensional in nature, such as budget amounts, are often depicted with two-dimensional objects, such as a dollar bill, or three-dimensional objects, such as stacks of coins, homes, or barrels. By using pictographs, artists can create false impressions that grossly distort differences by using the simple principles of basic geometry. That is to say, when you double each side of a square, its area doesn't merely double, but instead it increases by a factor of 4. Also, when you double each side of a cube, its volume doesn't merely double, it increases the volume by a factor of 8. Let's look at this pictograph that compares the percent of adults who smoked in 1970 to the percent of adults who smoked in 2013. The 1970 cigarette is about twice as long and twice as tall as the 2013 cigarette. So if you recall from your high school geometry class, volume is calculated by multiplying the base times the height times the width. Because of this, the volume of the 1970 cigarette is about 8 times the volume of the 2013 cigarette. But the actual percentage shows that the 37% smoking rate in 1970 is only about twice the 18% smoking rate of 2013. Edward Rolfe Tufte, an American statistician and a pioneer in the field of data visualization, recommends that we make all visual distinctions as subtle as possible, but still be clear and effective. He offers these principles in graphical displays of data. For small data sets of 20 values or fewer, use a table instead of a graph. A graph of data should make us focus on the true nature of the data and not on other elements such as eye-catching but distracting design features. Do not distort data. Construct a graph to reveal the true nature of the data. And also, almost all of the ink in the graph should be used for the data and not for any other design element. This is the end of Chapter 2, Section 3. Please move on to Chapter 2, Section 4, Scatter plots, correlations, and regressions.